All right, good afternoon. This is the part we all stop talking.
Thank you. All right.
Okay.
We're gonna have our seminar start up now. Similar to last week, we have 4 students who are going to be presenting on their experiences on summer internships prior to the start of the semester. So our first each talk will be about 15 minutes, so we're including questions, so we can get done at 5 o'clock. Our first speaker is Priyanka Pandit from she's a 4th year PhD student from the PRA research group. She has a bachelor's degree in mechanical engineering from Mumbai University. Worked on supply chain shortage risk assessment with the FDA, and then decided that nuclear is more fun, so she completed an internship at INL. And on the topic of quantifying software common cause failure using model-based simulation techniques, and has continued research on this topic. So it's all good. Take it away.
Quick question.
Click the power one. Yeah, you probably got to click on. It's probably stuck on Zoom, so you just got to do this. And now it should work. Try that. It's not working. There you go. You got it. Kind of.
Oh, I just used the.
Yeah, I just use this for now.
Yeah.
Okay, good.
Yep. Well, after that bit of troubleshooting. Hello, everybody. My name is Priyanka Pandit, as we went through. Today I'm going to present the research work that we completed at INL over the summer, which is verification of dynamic PRA models that we built in Embryo. Lots of words. Okay, so since this work was completed at the lab, I'm going to preface the PPT by saying the US government does not endorse or take responsibility for what I'm about to say. So yeah, that's that. So what is probabilistic risk assessment? PRA. It's a tool for assessing risks in complex systems and processes. And after we assess risks, we can develop mitigation strategies to combat those risks when they do occur. And it's used in many industries: nuclear, aerospace, transport. Big shout out to India that launched throw to the moon, no failures occurring there. Good PRA. So the NRC, which is the Nuclear Regulatory Commission, uses PRA to support all their decision-making processes. And so, really important stuff. And so how do we find out what can go wrong? How do we find out how likely is it to occur? So that's why we use the risk triplet. That's what this means. So we have the scenario that can go wrong, how likely is it, and what is the impact that occurs when it does happen. And PRA is all about answering that. And how do we do that? So what we do is we model the response of the plant as an accident sequence. And to represent this accident sequence, we use a event tree, and we also use one of the things we use is fault trees. So in short, an event tree is a sequence of events that are happening, and the frequency with which it occurs and the probability with which it occurs. So if you have an initiating, say the seminar started, and then you have a pivotal event, what can go wrong? So maybe the laser stopped working. So you have a pivotal event there with the probability, and the end state, which is core damage or bad seminar, can be here. So how do you calculate the failure of a system or a component? So that is represented by a fault. And we take the stop event and stick it over here. So now, the failure of a component and system can be a logical combination of many events. Say, for example, in this case, maybe the laptop stopped working, or the laser stopped working, or both stopped working. So this is how we represent the system. And so once we have all of this information, we can plug it to the risk triplet. Now, for the event sequence, the order in which these events occur in classical PRA is decided a priori by the analyst. So depending on a set of system and operator response characteristics, the operator will manually plug in these events. And the timing is not, if the timing is like discretely captured. So what it's gonna do is gonna bound the contribution from all the responses of the scenarios that were differing in the initiating event timing. So how do you overcome this? So we want to be able to use, we want to be able to integrate time into the event tree. So that's why we use dynamic PRA. So dynamic PRA is a tool that will link deterministic and probabilistic PRA. So it will automatically account for the system and operator responses. And one of those tools that I was working on was Emerald. So Emerald, short for Event Modeling Risk Assessment Using Link Diagrams, is one of the tools of dynamic PRA being developed at INL. And what they're just like in the research phases, they're using Emerald to research dynamic PRA. And at the heart of its engine is a discrete event simulator. And this is what the graphical user interface looks like. So if you go up to Google and type emerald.inl.gov, this is the website that you're going to be redirected to. And this is the demo project, which I've opened up here. So dynamic PRA also incorporates the event trees and the fault trees and all the basic events that I showed you earlier. But how does it do that? So dynamic PRA uses, or Emerald uses something known as a state diagram. So this diagram, or this pop-up here, that will encapsulate what state the component is in or what state the system is in. So here I've shown you a generic component, and it can either be in the running state, or it can be in the fail state, or it can be in the repair state. And each transition happens with a certain probability that we capture here in this dialog box. And also you can add conditions, like was the repair crew available to do the repair? And so you have multiple components, right? And the system that comprises of these components can either be in the running state or fail state, depending on the components and the conditions that are required to keep it successfully running. So that's encapsulated in the plant diagram. And so here here I've shown you that for the system to be in the OK state, both the components need to be running. One of the components need to be running. And if either one of them fail, then it goes to the down state. So that's a brief overview introduction to Emerald. And my job really there was to make sure that the calculations that Emerald gives you are indeed correct. So how much time did it take for the system to go from OK state to system down? Do we know that the answers that Emerald gives us are correct? Are they indeed the amount of time taken? So that was really my job. And to do that, we have two parallel paths. So the first one is building the classical models. So just your traditional component and the component fails. And the second one is we incorporate a little bit of complexity in it, where we have component, failure, maybe repair, maybe component was on standby, maybe repair crew was not available. And then what we do is we test this for all possible combinations. Single component failure, two components failing, two components failing in parallel, two components failing in series, standby. I'll not bore you with the list, but it's a big list. So yeah, and for the classical PRA verification, we have so just an example of an event tree and how it would look in Emerald. Your normal operations, you have the safety feature actuated, pour damage, and stop. And this is an example of incorporating a little bit of complexity with having repair and a repair crew available or not. And this is the equation we use to verify analytically whether Emerald gives us the right answer. So I might leave this for slide for question answers because this is just how you derive the availability equation for the analytical calculation. And then after running all of the models that we developed, most of them indeed will give you a pretty close answer. Not too bad, not bad numbers. However, when we hit the stage where we have a little bit of modeling disparity between Sapphire and Emerald. So for example, if you have like the common cause failure, the answers were yeah, they're not too close. They definitely did not fit within the standard deviation. And for the other cases where we had one repair person available, we ran into the same issue that they did not fit within the standard deviation. So we tried an alternate modeling approach where instead of modeling a component-wise model, what we do instead was we model the Markov chain. So this is what the Markov chain would look like. Both components work, one fails, one works, both. And the Markov chain gave us better results in all of the cases. So that was test 2. So that was the verification work we did. And there were 2 corner cases that we ran into for which Emerald definitely needs maybe a different modeling approach, or we need to look into its engine and see what's happening there. And that's what we're working on currently. Bunch of references, and that's all.
Do we have time for a few questions?
How do you qualitatively rank consequences in the scenario based on downtime or money it would like be to fix it? Like how do you rank one consequence over another?
That would really depend upon the analyst and like what criteria they have. So really export them. Or let me not.
Any other questions? Don't we go here?
So how do you tell if the Markov chain is mathematically more correct than the first approach, or just because it converges to the same probability?
I think the Markov chain would always give you the more like the accurate answer because it's a mathematically derived model, right? Like for example, if you have like a partial differential equation, you know for a fact that that is going to be the answer.
Good. Good. One point.
Do you consider the gradation in the probability of any component inside when you simulate?
So when you say degradation, you mean a component is like
Yeah, failure probability will be increased if it's at the time coding.
that's interesting. We didn't do it so far, but it would be very simple to go back and do it. So right now we have a transition we have a failure rate over here, but what we can do instead is have a variable. So x is a function of x squared maybe, like that's how it like if
Okay,
it has a
okay.
yeah.
You can set it
As a distribution. Yeah.
Any more questions for our speaker? Last chance. All right, let's thank our speaker. I got really scared there once I got 50 slides. I was like, okay, our second speaker is I'm trying to, sorry, I didn't have the last name on your biography, so I can. Edwin Aris, and I'm gonna ask you to pronounce the university.
Hacettepe. Hacettepe.
Hacettepe?
Yeah.
Okay, received his bachelor's degree from nuclear engineering from Hacettepe University in 2012. Spent 7 years in industry. Good jobs. Which allowed him to gain experience in project management, system and equipment qualification, and licensing a radioactive drug production facility. And then in his spare time, he completed his master's degree in nuclear engineering at NC State in 2021, focusing on detecting illicit nuclear activities in nuclear facilities. His current research goal is to develop an open source, web-based, parallel, and distributed probabilistic risk assessment model quantifier. And to reach this goal, he creates synthetic PRA models, uses generic PRA models for different types of nuclear power plants, benchmarks and profiles current PRA tools. Discovers and updates pre-quantifying, quantifying, and post-quantifying algorithms, implemented PRA model quantifiers, and add to the parallel running capability. So we're gonna learn a lot about PRA. So on that, over here, so 15 minutes.
Okay. Hi, everyone. Sorry for the fancy words. I did prepare that words for another purpose, but. So today I'm gonna try to build what Priyanka talked about, the PRE basic. Diagnostic and strategic plan for advancing the Sapphire engine. I'm gonna walk through the benchmarking, performance analysis, and upgrading the Sapphire engine. I had an internship experience in the reliability, risk, and resilience science departments. I strongly recommend if anyone are willing to do an internship at that department. This is the same disclaimer. So I'm gonna start with the motivation, why we did this work. Gonna briefly talk about what is Sapphire, and then walk through the methodology step by step, benchmarking, profiling, and upgrading the software. And then I'm gonna show up the results, what we get until so far, gonna wrap up everything in my conclusion. So we need a motivation to do this work. It is starting with all the probabilistic risk assessment applications started to demand high computational power. And unfortunately, most of the PRE tools were developed during you have never born, like let's say 18 and 19. So although the Sapphire, the one that has been maintained by the Idaho National Laboratory, has a lot of enhancements, but still a comprehensive analysis pending. So we do need a couple of things to edit. I'm gonna not delve into what are we need to save my time, but if we have something to improve, the solution is kind of obvious. Let's go and upgrade the engine. So, but to do that, we need a research roadmap that I'm gonna show you right here. I'm gonna get benefits and anecdotes. For example, if you are sick, let's say you are here, you go to a doctor, and depends on your situation, doctor is gonna do quick diagnostic or detailed diagnostic. And then he's gonna give you your treatment. Depends on the treatment, he's gonna give you a control, check that, and then whenever he feels okay, you are gonna good to go your normal life. We are gonna do the same methodology here. We have something to improve. So we are here as a researcher. We can do quick diagnostic, which we call it benchmarking, or we can delve into source code and do the profiling. Depends on the results, we can upgrade the software, and then probably we are gonna have a couple of test scenarios. When we feel confident, we can release the new version of the software. So Sapphire stands for System Analysis Programs for Hands-on Integrated Reliability Evaluation. It has a successor of another PRE tool. It's let's say, the latest version, still, let's say 8 plus, blah, blah. It's not so much important. The important thing is the methodology. How can we improve it? The first one is that I mentioned is the quick diagnostic. In the quick diagnostic, we are gonna just measure the CPU time, hold time, and memory usage, not gonna delve into source code. To do that, we need to prepare something which is we are supposed to configure our environments. We are supposed to prepare the engine, the Sapphire Solve engine, and then we need many input file to test it. For this work, we prefer to use BenchExec, a benchmarking tool, which is an open source. You can have access each piece. And then regarding the input file generation, we define 18 arguments. You can make complex fault trees by changing any of the arguments. For example, we focus on the gates, and gates or gates, k out of n gates. And also we start number of basic events from 100 to 5,000 with the increment of 50. And then we do also need to configure our tool that I mentioned, BenchExec. Here's the sample configuration. We need to define our limits. We do want you to do this calculation in your regular laptop. So we set the time 30 minutes, 16 gigabit RAM. And for the detailed diagnostic, this is the methodology for the profiling. We prefer to use an Intel tool, which is called VTune Profiler. Again, we set up the configuration, an engine, and pick one of the complex input files that we already created. And we delve into source code to find out the bottlenecks. Preparing the engine is not straightforward. Depends on the engine, the source code, which language they have used. You may do some additional work. Here, it's written in Delphi, so we need another mapping to convert this Delphi map file into the Microsoft PDB files. And then we pick a fault tree which has 310 basic events, which is quite challenging fault tree to be able to quantify in 30 minutes with the given resource. And then we pick the truncation size, the minimal cut set truncation size, 16, 18, and 20. For the upgrade methodology, I do create a success tree in this case. To be able to upgrade the Sapphire engine, this is an OR gate. So we can either update the code or benefit from parallel computing. Regarding updating the code, we can update the algorithm that implemented, or we can basically switch from 32-bit to 64 bits easily. Or getting benefit from parallel computing, we can get benefit shared data parallelization or distributed memory parallelization. Let's delve into results, what we get. Regarding the quick diagnostic benchmarking results, we noticed that Windows and Linux version are different. Windows is working perfectly compared to Linux one. But if we ignore the truncation probability for the Linux version, it also works perfect and able to quantify almost all fault trees. I also added line here, column here, to compare Sapphire results with another open source, the engine called Scram. And for the profiling results, when we increase the truncation size, we can see that for this specific fault tree, it's following a pattern, exponential pattern. And the thing that we consider is when we increase the truncation size to 20, quantifying this just one fault tree takes a day. So that's our kind of motivation. And then we did also identify the top hotspots in the code. These are some of the functions that are using around 65% of quantification time. So now we know what to do, where to focus on. And then regarding the upgrade, I showed you a success story. We started from the very simple one, switching the 32-bit to 64-bit in one module, and on average, we gain 29% speed up. So we put a diagnostic and strategic plan for the Sapphire, but it's also applicable for any software. And then we define the limitation, identify the hotspots, and make the initial improvements. The next step is adding the parallel computing and algorithm updates, and then we're gonna switch benchmarking environment from Linux to Windows, because all the users of the Sapphire is Windows-based, and they are building all the tools for the Windows machine. And then we are gonna include other quantification algorithm, common cause failures, and finally, we are gonna validate our findings with the real models, because they are all synthetic models. Thank you for your time.
Questions?
I put something funny up there.
You got a question?
It is so clear, so you don't have it.
So you're having all these individual methods of gaining, such as like the gaining 64-bit or increasing the parallelization. Do you quantify each of those individually, or are you only looking at the cumulative gains?
I am quantifying all the fault trees individually. So for the limit that I give you 30 minutes and 16 gigabit for each fault tree. So quantifying all the things sometimes take a week.
Yeah, question.
Very good.
Any other questions from the audience? Any questions? Actually, I forgot to mention, are there any questions online? Please raise your hand and we'll, or put it in the chat.
Thanks, everyone.
Okay, thank you. Okay, so we're moving on from the PRA phase of the seminar to the multi-phase research group phase of the seminar. Our next two speakers are going to be coming from that group. Our first speaker from this group is Taylor Grubbs, who was raised in Broadway, North Carolina, which is about an hour south of here. Originally studied physics at UNC Greensboro, got his master's degree here at State in 2019. After working on neural networks for a financial technology company, he decided to return to NC State in the spring of 2023 to study nuclear engineering and works in the multi-phase research group where he's working on simulations of two-phase flows with boiling water reactors. He enjoys rock climbing with his girlfriend. He enjoys Star Trek and geopolitics. And it was interesting when I first saw this, when I first read it, I'm like, your girlfriend's name is Star Trek? But yeah, but there was a well-placed comma there, so that didn't show up in the video. So so the floor is yours.
All right, thank you. All right, I'm talking today about my work I did over the summer at Lawrence Livermore National Lab. It actually has nothing to do with multi-phase flows. It's more on radiation transport. I worked with one of the transport codes called IMP. It's a Monte Carlo radiation or thermal radiative transport code. I'll explain more about what that is in a little bit. The specific internship that I was in, this DSTI, that's an acronym for the Defense Science and Technology Internship. The application is open right now. If anyone's interested, it's a really fun experience. I recommend it. Oops.
Sometimes.
Okay, here we go. All right. So first, what's the motivation for modeling a detector? So here on this picture here is a zoomed out version of the National Ignition Facility's target chamber. If you don't know what that is, it's a really cool experiment where they shoot like almost 200 lasers at this little gold capsule called a holograph, and fusion stuff happens. It's really kind of neat. But yeah, this is like yeah, I really like Star Trek, but like this is like real life Star Trek here. This is like really cool. But yeah. So motivation for this is this Dante X-ray detector. There's like there are two really massive like X-ray spectrometers positioned on different sides of the target chamber. And they do exactly what it sounds like. They detect X-rays that come off the whole ram during an experiment. And you get a lot of valuable data from that. These bottom two graphs show you the X-ray power and the X-ray spectrum that these detectors can give you. And a goal of this, like eventually from this type of work that I worked on, goal of this is eventually you'd want to reproduce those graphs, right? You'd have your codes doing simulation of the fusion stuff, and then you plug in this thing and you want to reproduce those plots. And if you did, that tells you that you kind of know what you're talking about. So how do you model a detector in a simulation? One way to do it is you take your Monte Carlo radiation transport simulation, where Monte Carlo simulations, you basically have lots of little particles that are just bouncing around randomly, and you kind of let them run through your system, measure them. The issue with that is, you could, if you wanted to model a detector, you could just label a region of your simulation as the detector region, and whenever a particle hit that detector, you would count it up, and that would be your signal. The unfortunate thing is, if your detector is like meters away, like in the case of like NIF, like this is a very rare thing to happen. You're not going to have a random particle come off and then hit that detector very often. So what you then need to do is you would need to simulate like billions and billions of these things, and we don't have time for that. So alternatively to that, what you could do is you take a set of particles and you force them to travel directly to the detector. And as they travel through your material, you can change these particles' weights or the parameters to replicate the real effect or the effect of real particles as if they came right off of the material itself and traveled directly to the detector. I'm going to explain more about what that means, but that's like the broad picture of like what I actually did in the code here. So here's a more like well-defined like description of the problem. So thermal radiative transfer codes like IMP can be used to model X-ray detectors like Dante, but they require, before the summer, they required a post-processing tool like Visit, which is this visualization tool that can do ray tracing. What you could do is do this ray trace through your system to calculate an intensity at a detector. Unfortunately, this required you to write out to disk the emissivities and the opacities to, you would need to write this out every time step, and that becomes very, very expensive when your simulation becomes larger and larger. And so the goal of the summer was to add this same type of detector modeling into IMP so that it can run while the simulation is running, and you don't have to do all these expensive disk writes. And that's just the IMP mascot, and he's kind of cute. Okay, yeah. So these two equations here, the thermal radiative transfer equations, what they're telling you is how light travels through a material, and then how that material's temperature changes. So this first equation is the intensity of light going through a material. The second equation describes how that temperature, or how that material temperature changes over time. The important one for me this summer was this first equation. These blue terms are kind of like a derivative of the intensity called like the streaming terms. This red term is at loss due to the opacity of the material. And these green terms are sources coming from light emission from the material and any other sources you might have. These are neatly colored to group them together. So you can take this equation and you can use a method of characteristics to turn it into kind of a simple ordinary differential equation where it's neatly organized into your red term to your opacity, and then you have a source term, which is the emissivity. And if these, the opacities and emissivities are constant, you have a very nice, easy solution. Again, the intensity, so along a path inside the material, you can calculate the intensity due to two components, which is the, the attenuation and then the emission. And so you can do this with something like Visit using a ray tracing type of system. And this kind of schematic shows how that works. And so each of these little squares are little simulation zones. Inside these zones, you have constant opacities, constant emissivities. And as your light ray goes through them, you calculate an attenuation factor and an emission factor, and that adjusts your intensity as the light ray goes through the material. And then on the other side, you can tally up those rays and create a calculation of your intensity. So the emissivity largely comes from thermal emission, and if you assume local thermodynamic equilibrium, this is what that looks like. It's got a temperature to the fourth power. That's kind of neat. And it's nice, it's simple. You can easily program this in and just go. So yeah. Yeah, and you can see these green zones are places where there's a lot more emission. So your light rays get more intense and brighter. And these red zones are more opaque, and the light rays go dark. You lose that light as it travels through. I'm not gonna go through every detail here. Just want to point out that IMP is a Monte Carlo transport code that uses something called the implicit Monte Carlo method. And the IMP code contains something called diagnostic particles, which are these like pseudo particles, which can be used to model rare events. And that's what we used for this for this project to calculate these like ray traces. So yeah, the big changes that were made to IMP this summer were these diagnostic particles were modified to generate them at something called a source plane, and then they would travel through your whatever material you have to something called an image plane, and these planes are split up into like little squares. These are exactly like pixels on a camera. You can imagine them the same way. And as these particles travel through the material, you have their particle weights adjusted to account for all the intensity adjustments that I mentioned previously. And yeah, a lot of the work was just modifying the code to keep those emissivity values propagating between time steps. It's probably more relevant for the people who actually use IMP, but the point here is to say that it's very easy to kind of just plug this stuff into, create these source and image planes and then generate, radiography data on your simulation. For the test case that I came up with is just two concentric cylinders of different material densities. On one side, you have a non-zero temperature source. So what that does, it creates light that propagates through the system. On one side, we have a source plane which shoots these diagnostic particles through the cylinder. On the other end, tally it up on the image plane to generate, power and energy spectrum and other things. And I can easily rotate the system around to generate images of the object at different angles. That's what I do. But first here is the total flux or power at the image plane. And then here in the right is the energy spectrum. And you can see in blue is the IMP code, and red is the older method using Visit. And they both match up very, very well. And then here is an example of actually using this to generate like radiographs, like X-ray images you might get at like a doctor's office. And you can see like these are different images taken at different perspectives, rotating around the cylinder. You can see over here, this is the back end, which is a little cooler, and over here is the hot end, which is why it's bright yellow. So to summarize, a new radiography capability was added to the code, which can account for both attenuation and self-emission in material. At the image plane, you can tally up these diagnostic particles, which can then be used to calculate images, emission spectra, and total flux versus time. And it looks like all of these things are very good agreement with the older methods using visit. So that's all. And this is my disclaimer, it's at the end.
Okay, questions for our third speaker?
So some of the codes that you talked about at the very end, final slide, like Cole.
Yeah.
I was curious, are those improvements on current methods that you're using now? Is that software improvements or?
So no, so yeah, I didn't talk about this because it's more for, yeah, the future work part here is more for the people over there, but yeah, you would want to incorporate this functionality into those codes as well, because those are like the bigger codes that actually are running like the whole ICF fusion like simulations. Yeah. Yeah.
Is there any reflection between the boundary of the opaque and the high emissive region, or is it kind of ignored? Like when the light goes through it, do we count reflection, or do we say it probably doesn't matter?
Like
Just
in
keep
here,
lights back,
or let's see, in here.
two more, I think.
More.
There,
Yep.
yeah, is there any?
Oh,
Like,
so yeah, when the particles, so yeah, the way it kind of works is when the particles hit the like the tally area,
Yeah.
like image plane, they just keep going and zoom off to infinity, and then they get killed.
there's no real reflection.
No, yeah, these diagnostic particles are very kind of like pseudo particles in a way. They don't really interact with the physics of the simulation. They just pass through and measure stuff. Yeah, yeah.
Any other questions? So this is mainly computational. Were you on site or do we use it all the time?
Yeah, I was on site. But yeah, I just sat in the computer all day. But yeah,
So being a Star Trek fan,
yeah,
you did get these, because they filmed scenes there.
Yeah.
For the one for a couple of the.
Yeah.
new movies,
it gets
right?
into darkness. Yeah,
Yeah.
I was. Yeah, we got to see the. Didn't get to see like inside the target chamber because they were doing experiments, but we got to see the whole NIF facility. It was really cool. Awesome.
What's that?
That was pretty nifty, wasn't it?
Yeah.
You're not allowed to ask any more questions.
For the video.
All right, any last questions for our speakers? Okay, let's thank them one last time. Our fourth speaker is also from the multi-phase research group here at state. Nicholas Meacham is a third-year student working in computational fluid dynamics. Part of the multi-phase research group. Completed his BS in mechanical engineering at the University of Utah. And is currently in 2021 and is currently seeking to improve direct numerical simulations of boiling phenomena by increasing the resolution of interfacial mass transfer while maintaining conservation. I'm also going to apologize. Mario's going to take the Q&A at the end. I got a conference call at 5, so I'm gonna
That's fine.
stick around for the whole thing. I apologize.
That's fine, by me. But I appreciate the heads up.
So the floor is yours.
Thank you. So thanks for coming to the seminar, everyone. Like he said, my name's Nick. We're going to be presenting today on kind of a crazy 2023 for me. I did an internship at Oak Ridge National Laboratory, again, doing fluid dynamics research. And I also attended the Nuclear Innovation Boot Camp a couple of weeks ago, which I'll also be presenting on. Hopefully we can get more NC State students to attend that. So some background on the internship portion. The high flux isotope reactor core is shown here on the bottom. This is a streamwise view. It's an involute plate reactor. If you're unfamiliar with what an involute is, you can think of it as a section of a spiral or an arc with an increasing radius of curvature as you move along the span. All right. So coolant passes between the involute plates that contain uranium within them and kind of creates this funky channel shape, which we're very interested in investigating. All right. So I've been part of this project for a few years now. So we've previously conducted direct numerical simulation of the realistic geometry in 2 of its dimensions. We didn't capture the entire streamwise length because that's much longer than the other 2 dimensions. And that just isn't computationally feasible, right? So we just did a little less than 1% of the total channel length and imposed periodic boundary conditions on the inlet and outlet. If you're unfamiliar with that, it just copies the solution from the outlet and imposes it on the inlet so that we can maintain any turbulence that we develop within the simulation, right? It was an extremely expensive simulation. We generated a 10 billion element mesh and it necessitated 50,000 processors to resolve it. So it kind of brings us to the motivation for the internship, right? Which was to develop a RAND simulation, that's a Reynolds average turbulence model, which is capable of delivering the accuracy of our DNS results, right? Which, you know, would enable it to be more useful in engineering scale applications, as opposed to just kind of our research and academic based DNS, right? So the plan was to adapt an existing RANS model to provide the same accuracy, right? Much easier to adapt an existing one by adjusting model coefficients and whatnot than inventing our own. So since the RANS was so much less computationally intense than the DNS, we were able to simulate a longer portion of the channel and get rid of this sort of cycling boundary condition which we had for DNS. And we could just simulate a longer portion and wait for the flow to get fully developed essentially before we took our statistics, right? So the numerical methods which we used, we switched to using OpenFOAM as opposed to Dr. Bolotnoff's much beloved FASTA, which entailed a little bit of learning for me. We used the simple algorithm, which is a steady state solver, so it doesn't do any transients or fun things like that. We selected the K omega SST turbulence model for a baseline. The K omega SST model is a fairly robust model. A lot of different industries use it, especially aerospace, because it combines the free stream strengths of your standard K epsilon model and the near wall strengths of a K omega model, right? How these types of models work is they solve 2 additional transport equations for the turbulent kinetic energy, which is K, and the dissipation rate, which depending on how you formulate it is either omega or epsilon. In this case, it's omega, obviously. Like I said, the domain is 50 times longer than the DNS domain. And also it's only 500,000 hexahedral cells, right? As opposed to 10 billion. So it's far more computationally affordable. We don't really need a supercomputer to run these types of simulations. So that's really the attractiveness of doing this kind of work. Unfortunately, in the 3 months I was there, we weren't able to completely solve the problem since turbulence modeling is a little difficult. However, we were able to do quite a bit, including just some general baseline comparisons between the K omega SST model in red and our DNS results in blue. These have all been normalized, so but normalized so that they're on the same scale. So we can see that the velocity profile in particular is an important one. It's a little bit flatter, not too terribly different, which is a good thing, which means, you know, the turbulence model isn't absolutely terrible. But it's all of the profiles are a little bit flatter than we saw with our DNS results, right? And our hypothesis for this is that the eddy viscosity down here, which is sort of the major term which gets passed into your velocity and pressure solvers from, the turbulence model itself is peaked at the center of the channel as opposed to having this sort of double hump structure, which we saw with our DNS case, right? And so our theory is that this pushes down our velocity profile, making it a little bit flatter than what we saw with DNS. We conducted several sensitivity studies on model coefficients. We put the equations down here so you can see several different model coefficients in here are sigma k, alpha, beta, sigma, omega, and gamma. We conducted sensitivity studies on all of those, and we found that the most promising coefficients for exploring for changing in the future are the ones that are related to eddy viscosity. Because, changing those sort of puts the profiles into a little bit better spot for what we expect from our DNS results, right? So our next couple of steps are to try implementing a wall distance based correction factor on those model coefficients that we previously identified to see if we can, correct those just a little bit and magically get the DNS shape profiles that we're trying to get. We also want to explore adjusting the boundary conditions, which we apply for the K and omega equations. Obviously, since we're solving more equations, we have to implement new boundary conditions for those. And those are a little, we have some wiggle room to adjust those, we'll say. Further work, more further on in the future, we are targeting doing temperature resolved simulations so that we can fully characterize the reactor heat transfer in HIFER. And thus far, since we've only been paying attention to one channel due to, computational necessity, we would like to study some interchannel interactions, especially if we're going to target heat transfer. All right. So that kind of wraps up the internship portion. Now I'll talk about the Nuclear Innovation Bootcamp. We'll do some hard gear switching here. The Nuclear Innovation Bootcamp, I'd highly recommend for people to apply to. It is an entrepreneurship-based bootcamp for people interested in nuclear energy, right? So they accept people from a wide variety of backgrounds. In this cohort this year, there were politicians, lawyers, a lot of nuclear engineers, obviously, since we're the ones who seem most invested in nuclear power, as well as regulatory folk who work for IAEA and other regulatory bodies like the NRC, right? And I'm sitting here in green in the front row. So there's your proof that I actually was there. It was hosted by Tokyo Institute of Technology. It was really cool to go to Japan. Next year it will be hosted in the US. I've heard tentatively that they're looking at North Carolina, but not set in stone, as I'm not a representative of NIA. Here's just a sampling of some of the activities which we did while we were there. Obviously, a very heavy focus on sessions and panels, including, discussing the current nuclear landscape, creating viable business models and convincing financial models, as well as current nuclear startup technologies, how to speak with credibility, which hopefully I'm emulating right now, and several sessions on Fukushima cleanup activities, because obviously we were in Japan and that is a very heavy focus right now. And being around all of these professionals, most young, some old, obviously the people presenting were mostly older. It provided several networking opportunities, which we took full advantage of while we were there. And then sort of the capstone on the 2 weeks while we were there was a group project, which I'll discuss on the next slide. And the free weekend for tourism, I took full advantage of, so we're good there. So the group project, the objective of this is to pitch a business model that fills a need in the nuclear energy industry currently, right? So for example, my group, we tried to target decommissioning cost estimating, since cost estimates for decommissioning projects are all over the map and not particularly good in our current day and age. This is a picture of my group. I unfortunately had COVID at the time, so I'm on Zoom with the judges for this. The deliverables for the group project are a business plan, a financial model that should be realistic enough to be convincing, and a pitch presentation. The prize this year was a $4,000 travel voucher to the IYNC 2024. I don't know if that's every year, but it was for this year. My group didn't win, sadly, but we were up against stiff competition, we'll say that. The highlight for me personally was we got to go to Fukushima Prefecture in order to visit the Naraha Center for Remote Control Technology Development, which is essentially a robotics manufacturer that's helping with Fukushima cleanup activities. And then the morning after that, we toured the power station itself and learned about their current wastewater treatment, which I'm sure everybody reads on the ANS Smart Briefs about weekly. In addition to more details on the accident itself and the activities which they're trying to undertake to speed that along. So I've included just some of the pictures to wrap up here to illustrate, the power of the tsunami that hit, that just completely torqued that container like a soda can. I show up in a couple of these pictures. The top center one is the units 5 and 6, which were not completely devastated by the tsunami. And on the bottom right is the tritiated water that everybody has heard a lot about. They let me hold it. They didn't let me drink it. Yeah, and of course, just 100 yards off from units 1 through 4, they have a big detector that shows you what your dose rate is there. So with that, I'll be more than happy to take any questions you have. Questions?
So on the business aspect of this trip that you went to, did it focus primarily on pitching viable business plans, or were you also looking at, say, project management and planning mechanisms?
Yeah, so unfortunately, in 2 weeks, we weren't able to explore like an established business approach, right? This was mostly focused on just, Shark Tank type activities, pitching a business, getting a startup going, things like that.
Else?
Yeah.
With the new method that you are proposing, are you losing any accuracy compared to the very high computational demanding one?
Yes, we are definitely going to be losing accuracy, just kind of by the nature of going from, a method where we resolve every turbulence scale, all the Kolmogorov scales, if you're familiar with those, to a method where we're implementing a lot more subgrid modeling, right? But that's the impetus for it, is we're trying to make it better, right?
But for now, you are not able to measure how much you are losing.
Yeah, for now, we haven't gotten to any uncertainty quantification yet. We haven't even gotten to a model that is, well, we've gotten to some that are a little bit better. We're still working on it.
One last question.
They actually talk about this in first year, how hiring is for.
Yeah, so in case you didn't hear the question, it was how much did they actually talk about nuclear startups? They discussed mostly existing companies, like they brought in people who founded other startup companies to discuss what technology they're using, which, was extremely interesting because we don't usually hear that in the academic sector, right? However, it definitely gave us some perspective on where there might be some market gaps. Particularly, we heard a lot from some fusion startups. Like, I can't remember the name of one in particular, but it used a technology that they called the Z-pinch that I thought was very interesting.
All right, everyone, let's thank our speaker. So now, first one next week's seminar, I don't believe we'll be in this room. Please look out for my email, we'll be in a bigger bathroom. We're expecting a lot more people and there's still refreshments.
Okay.
No.